Okay. All right. Well, let me then give you a sort of a brief introduction. So Cem Karan is a PhD student here at the GRASP Lab. He's also a full-time employee at the Army Research Lab, a little bit south of us, and he has been looking for quite a while at these sort of robotic communication networks and various approaches to this particular problem. So with that, I'm going to let him take it away and talk a little bit about a survey of relevant approaches.
Well, thank you, CJ. This is a survey. It's deliberately aimed to be a mile wide and about 1 millimeter deep. So if I don't cover your favorite topic, I apologize. Let's see, try and get this thing working. So what are we going to cover today? Just a basic introduction, explain the problems that we're working on. That I expect is about 5 minutes. A survey of the current approaches and a couple of deep dives here and there where it looks interesting. Finally, concluding with some concluding remarks and then leading up to questions. So, what are we talking about? Communications methods when radio is not ubiquitous and guaranteed. This means places where you can't guarantee that your Wi-Fi is going to work, or where it will work for short periods and not for in most areas. As an example, think of the hallway where you might have multipath fading. So as you're going down a straight hallway, all of a sudden you have good comms and bad comms and good comms and bad comms. Anything like that where radio is difficult. This is not a dissertation defense. Shameless plug, my defense, if all goes well, will be in April. Please come to it or don't, whatever, it's your choice. Why do we care about communications? Well, it allows us to coordinate our actions with one another. We could coordinate without comms, but it's much more difficult. It allows us to be able to adapt to dynamic changes to the goal. So if our robots are out in the field doing something and suddenly the world changes, like one of them rolls across a mine, all the others can quickly learn about this fact. And finally, it makes us much, much more efficient at what we do. So a few motivating examples. Every year, there's a mining disaster somewhere in the world. We only hear about some of the really big ones. A few years ago, I believe everybody heard about the mining disaster where there was like 54 miners trapped in a mine in Chile. And after a while, after I think 30 or 40 days, they were extracted. That particular disaster, they weren't able to get people in, but they were able to drill a borehole within about 2 days. That borehole was large enough that we could drop small quadcopters straight into there to do exploration if we needed to. And then those quadcopters have to have some way of communicating what they discovered back to the surface, which is not exactly easy through many hundreds of meters of ground. Then there's also war, which is a disaster multiplied by the fact that if anything can go wrong, it will go wrong because your enemy will make absolutely certain that it does. And finally, as I mentioned earlier, DARPA's Sub-T Challenge, which I believe a number of people in this group are probably either a part of or interested in. So you're therefore interested in communications. So what's the problem? We have radios, right? As I mentioned earlier, radios don't always work. Water turns out to be a really efficient absorber of radio energy. It's why microwave ovens work on microwave energy. And then you also have multipath fading and other effects as radio waves bounce around underground. That means you might have a radio that in free space, and when I say free space, I mean like outer space, would be good for many, many, many miles. You're talking about a few meters at best underground. Then when you go back to war, there's jamming. There's two different types of jamming. There's the accidental jamming where, in a large echoey room, we all tend to start raising our voices, trying to talk over one another, and now we're all jamming each other. Well, same with radios. If you have radios where you can control power levels. Then there's also just the standard jamming we all think about when we think about war. All of this leads to network partitioning, where you'll have small knots, sometimes of robots, sometimes one robot that has in its own partition, unable to communicate with other partitions. What do you do in this case? So I'm going to step sideways and I'm going to explain how I'm going to organize this whole talk. And I'm going to organize it slightly differently than you might expect. I'm organizing it around a database theorem called the CAP Theorem. The CAP theorem applies anywhere you have replicated distributed data. So what you were talking about just earlier with your distributed database, the CAP theorem applies. And it stands for consistency, availability, and partition tolerance. Consistency means that every replica has the same data in it. Basically, has a copy of the same write that any one replica had. Availability means that you can mutate any replica at any time. It's not locked for some reason. Partition tolerance means that you can your system will continue working even though you don't have network communications between the replicas for some reason. So the CAP theorem says at most you get to have two. Now I'm fudging a little bit. If you know the CAP theorem well, you know that there's some caveats, but I'm trying to do this from a practical robotics point of view. And this is how I've organized the talk. So first, I'm going to talk about traditional schemes which try to prevent partition at all costs. Then newer schemes where some state information may be out of date. These are like eventually consistent systems. I'm not going to talk about read-only systems. They're not as interesting. We can do them, but they're just not that interesting. So now we're coming to the actual bulk of the talk, why you actually came here. Partition intolerant systems. There's a lot of schemes that have been formulated over time for this. I'm just going over a few of them. You can end up having a priori radial maps or some other form of mapping, and then do lots and lots of offline planning to try to develop a guaranteed strategy that will always work, or be able to explain when your strategy will fail. A couple of forms of this are pursuer evader games and geometric Steiner Tree approximations. Gradients, which I'm sorry that Dr. Ribeiro isn't here because he did a lot of good research in this, where you develop some sort of artificial potential field and then just calculate the gradient and follow the gradient, either uphill or downhill, in a way that should ensure that you always maintain connectivity. There's K-hop neighbors, and there's various forms of this. I'm going to go into one particular form, but the idea is that you have a partial graph of a partial connectivity graph that's maintained at all times of your local neighbors. So you might know your immediate neighbors and your neighbors' neighbors, but no further out than that. That's where the K-hop comes over. And there's a heck of a lot more than this. Okay, now I'm going to do a slightly deeper dive. I'm talking about pursuer evader games. There's usually in the literature, there's three types of robots: an immobile base station, an evader, and some number of intermediate robots that keep the base and the evader connected. Now, the reason they're doing pursuer evader games is that the evader is supposed to mimic the worst case scenario. The assumption is that if you can always keep a evader, a robot that's deliberately trying to break communications, in contact with the base station at all times, then anybody who's less unfriendly is also going to be kept in contact at all times. However, there's many different types of pursuer evader games. The simplest ones do a chain of robots, so they always have to maintain a particular ordering. There's mesh versions. Sometimes the environment has obstacles, sometimes the environment is non-convex. It gets as complex as you want it to be. We're going to do a slightly deeper dive on one particular formulation. Here's the name of the paper. The idea behind their formulation of the world is the world may be non-convex. It may actually have obstacles, although I haven't shown it in figure 1. They discretize the entire world into a series of cells, and they discretize time. This becomes important later on when we try to calculate the big O notation for it, because, well, we'll get to there shortly. They have M mobile routers, one evader, and one base station. And although it looks like a chain here, it's not necessarily a chain in their algorithm. For their communications model, they have a priori map, which says that is pairwise between every cell, saying that either those two cells can communicate or they can't communicate. So that's where discretization comes in. Okay, so here, their basic algorithm is they're using dynamic programming to optimally place routers at every single step, and they're pre-planning this. The only issue with this is that you can see the big O right there. It's the number of discretized cells to the number of routers. So unless you have very few routers or very coarse discretization, it just doesn't work very well. Yeah, here's some of the very speeded up tricks. Fewer routers, coarser discretization, clever discretization, where they end up making convex cells that cover very large amounts of space. But they're all tricks, and your big O of n to the m remains. Geometric Steiner Tree solution problems. Now, I don't know if everybody's heard of geometric Steiner Tree. If you know about a minimum spanning tree, it's the same idea, except that you're allowed to physically pick up and move a certain subset of the nodes around wherever you feel like. And you can add or, well, there's a subset of nodes that you can add or remove as you see fit in order to be able to reduce the cost of the minimum spanning tree. Unfortunately, the distributed Steiner tree is NP complete, so we can't really solve it too well. Gradient-based approaches. Like I said, there's a lot of gradient-based approaches. They all do the same thing in the fact that they're finding a gradient, but the particular thing they're measuring changes all over the place. So you can have signal to interference ratio, signal to noise ratio, any other ratios you feel like. You can have artificial fields where you're calculating like link reliability, or you can do something really clever involving fielder value maximization. The fielder value is the second smallest eigenvalue of a matrix. The connectivity matrix, which is the Laplacian, it's a Laplacian matrix. So if people want to know, I'll explain more later, but if I go too deeply, I won't get this talk done in time. So I apologize, I'm going to continue forward. Then here's what we're actually going to go into. K-hop neighbors, where you're maintaining a limited connectivity graph for each node. So each node will know at most K-hops out and makes the best decision it can based on its limited local knowledge. Good does not always mean optimal in this case, though, because it's not just a question of only having part of the knowledge and part of the information that's available. It's that you might have to make a decision within a certain amount of time, or while expending less than a certain amount of energy. So a lot of these decisions are pretty good, but not provably perfect. So now we're going to do a deeper dive into this particular paper. They use an algorithm to try to guarantee that no node loses connectivity by maintaining this two-hop connectivity graph. And the idea is that you figure out your immediate neighbors, your neighbors' neighbors, and then you find the intersection for each of those sets. And then you have to guarantee that the intersection is at least size k. So if we look at these two graphs, if I want to make certain that k equals 2, you can see that nodes A and B on the left-hand side clearly do not have an intersection of neighbors that is greater than size 2. A only has one neighbor, B has lots of neighbors, but it doesn't share enough neighbors with A. Now, on the right-hand graph, you end up seeing how I broke just one link, the GH link, which has all of a sudden caused all these other nodes to have too few neighbors to be able to move. I think I accidentally missed that part. The whole point of the algorithm is that when you fall below a certain number of neighbors like this, you're no longer permitted to move. So on the right-hand side, only D and C are permitted to move. Now, the issue with this particular algorithm, although it's great in calculation, it's really fast to solve, it's very easy to fall into a position where suddenly nobody's permitted to move. So, other limitations. If you're trying to absolutely guarantee partition never occurs, you can't guarantee it. What happens if your goal is so far away that you just can't stretch to reach it? Well, your mission fails. What happens if you have some kind of jamming or some other issue occur? Now you have network partition. Now you have to have some sort of fallback solution. If you discretize space, well, we already saw one issue where it was big O of n to the m, which makes it impractical. But other forms of dynamic programming and other solutions also tend to grow fairly quickly like that. Gradient descent. This is a lot more practical, but you have to be very careful about how you choose and how you set up your fields. It's very easy to create an artificial potential field which guides you into a corner somewhere, and you just can't get out of that corner. Again, I was hoping that Dr. Ribeiro was over here because he actually has done some research and came up with some clever solutions that allow you to drive away from corners. With the K-hop, if you break a link, now all your nodes are immobile. Now what? All right, so if you can't have a guaranteed partition-free scheme in all cases, how about having a scheme where you accept and permit partitions and then just deal with it? Two of the most basic ones out there are flocking and data mules. Now, data mules are closest to my own work, which I'm not going to cover over here. Again, if you really are interested, come over and look at my dissertation defense. With flocking, you don't have any directly shared state, so there's no inconsistency. All you're doing is some very basic neighbor rules. It's fully decentralized, which is great. So you've managed to solve the problem, except that you have very limited behaviors and very limited functionality. You can do things like getting all of your nodes to be traveling the same direction, or if you're lucky, you might be able to get them all to be able to pick up an object and move it in one direction. So because they're relatively limited, people stopped studying them some time ago. Data mules are more interesting. The idea is that you have a large number of immobile units, which are the sensors, and a few mobile units. You usually know where all the sensors are in the whole field. Your mobile units, the data mules, are big, heavy, and generally considered immortal by most of the research that I've read. And their goal is to either minimize the latency of all messages that are delivered or minimize the energy usage of the data mules driving around. In general, these systems all reduce some form of the traveling salesman problem. So they all end up being NP complete one way or another. And now we're going to do a deeper dive into just this one paper right here. Let's see. Okay. This particular paper is trying to solve something called the data mule scheduling problem. If you look in figure 3 on the far left side with the path selection, it'll give you an idea as to what's going on. What you have is a field of nodes, each of which have a communications range. The data mule's job is to figure out a way to be able to travel through this field in the least amount of time and pick up all the messages and deliver them. Now, the problem with this is that it takes time to travel to pick up a message. Message communications is not instantaneous. So as it's traveling through node B's range, it may have to spend more time in that area in order to be able to pick up all the messages, or it might need to spend less time. So it does this by adjusting its speed, and then it does a bit of job scheduling in order to be able to determine, finally determine its best trajectory. The problem is that this particular problem is actually harder than NP complete. I don't remember the exact complexity class. The paper didn't say it. But in order to find the true optimum, you have to be guaranteed that the jobs that are you need to know a priori what all the jobs that are being scheduled are. And you'll have to iterate because each one of these sections, path selection, speed control, and job scheduling affect each other. So you could potentially have to iterate forever in order to find the truly optimal path. So what the paper did to solve this is they said, okay, we're just going to iterate once. We're going to do a single pass through so we can be done with it as quickly as possible. Also, we're going to assume that speed control and job scheduling are solved problems, so we don't have to worry about them at all. Finally, we're going to assume that the motion equations allow the data mule to loiter in a particular location forever. So where you might be thinking about data mules where they're ground robots, where we can just stop them, but they could also be UAVs, in which case they have to fly through an area, but they can't actually loiter in that area. So with these assumptions, they're able to solve the problem because now it's just a variant of TSP. So the variant it turns into is what they call the label covering tour problem. On the left-hand side, you see a bunch of nodes and the communications ranges. S is the start node or the data mule. On the right-hand side, you see the nodes again in a communications graph, a complete graph. And the edge labels are what the S node would pass through if it would pass in that particular direction. So if you see in the right-hand side going from S, from its current start position to node number 2, along that edge, you see the label 1, 2. That's because it'll be cutting through the communications path of node 1 and node 2. So the label covering tour problems, how to be able to cut through all of the cover all of the labels completely. As you can probably guess, this itself is yet another NP-complete problem. So yeah, Pro is just TSP, which means we've reduced its complexity class from the original class, but it's still NP-complete. It's still using data mules like this is fairly brittle, because if you only have one data mule and it fails, then your whole system fails. It has very high latency because if you're just rolling and not forwarding messages through to one collection area, you are not utilizing your communications bandwidth to its best ability. And finally, the sensors are all immobile. The idea behind this is that most of the data mule literature, they just assume that not only the sensor is immobile, but their locations are well known. So now it reduces down to the data mule just trying to discover the best path through. So I know that was a mile wide and an inch deep, but I'm hoping that gives you an idea as what the problem is really involving. Basically, this is a hard, meaning undecidable problem. There will always be cases where we cannot decide if we're going to be able to solve it. In the simplest case, all you have to do is think about a robot rolling into a closet and somebody closing the door behind it. Without more knowledge, you don't know, if you don't know when they're going to open the door, you can't decide if the robot will be able to go out and actually carry messages around or not. You're lacking certain information. There are a lot of different ways of approaching the problem. I will be showing a couple in about a month or so that I've tried. Go forth and do research. Find something, think things through. Oh, and come to my dissertation defense if you're not bored out of your skull listening to what I've been saying so far. So any questions?
Okay, so thank you, Cem. I think, as you said, you've covered a lot of ground in a short amount of time. So I suspect that we do leave some time for people to probe. Let me just sort of get it started since you've opened this up. As you were discussing previously, you were talking about the use of the Fiedler number as a criterion for deciding on motion of platforms and the like. So since we've left time available for discussion, maybe it's an opportunity for us to go back and talk a little bit about some of those that approach in particular, and perhaps others.
Okay. That approach I first learned from Ethan Stump's dissertation. The graph Laplacian is a measure of is a way of describing connectivity. It is an adjacency graph where every element in the matrix is a 0 or 1 normally. The diagonal is the negative of the row sum of all the other elements in the matrix. Now, it turns out that if you do this, and then you end up finding the eigenvalues, the whole thing, second smallest eigenvalue, it'll be termed the Fiedler value. If it's positive, it means that your entire communications graph is connected. Now, it turns out that if you go for a slightly more nuanced adjacency graph, where instead of having just a 0 or a 1 entry, you have values between 0 and 1, where 0 means it's disconnected and 1 means totally connected, and the values in between obviously meaning some measure of connectivity that's less than perfect, then your feedback values positivity tells you how strong, how well connected you are. So now you can end up using something like that to do a gradient descent method by trying to make moves in a particular direction, calculating out what your feeler value is. And if it's getting better, then clearly you're connecting more strongly. If it's getting worse, you're connecting less well. That's that particular approach.
Okay. All right, fantastic. Any other questions, comments, concerns from the audience? Again, we have a couple.
Yeah, I had a question. So first of all, nice overview. I like the talk. It seems like the way that you presented it, there are kind of two parties. There's the connect everyone all the time party, which is a significant, significantly limits the mobility of the agents in order to maintain connectivity. And then there's the other side of kind of the data mule that you were describing, where agents really aren't connected at all, and perhaps there is a mobile agent that is going around and collecting sensor readings. And so I'm wondering if you've come across work, or if you have thoughts on things that live in the middle, where you have mobile agents, but they allow kind of intermittent connectivity.
Come to my dissertation defense. You're basically asking me about my dissertation. I only started a stab at this. I did not realize how difficult this problem was going to be when I first started it. So for me, what I've got is essentially, think of it as a very large number of data mules and a very small number of sensors, and try and figure out how to be able to optimally connect all those together. It is much more difficult than I ever expected it to be. So if you really want to come over and see what I tried, I'm more than willing. Well, of course, I'm going to be doing my dissertation defense, and you can watch, or if you want to contact me afterwards, I can tell you everything that I've got so far. But as far as I can tell, there is no magic bullet. The problem is that once two nodes are out of communications, once you have network partition, you are making guesses, making estimates as to what the other network partition is currently up to. If you're lucky, you have some sort of clever fallback plan that will ensure that you can all heal your network together, even an arbitrary period of time afterwards. And those plans don't have to be all that, when I say they're clever, they don't have to be that clever. It can be as simple as, you have a series of rendezvous points that you have as fallback rendezvous, and everybody rolls back to them if they lose network connectivity. Unfortunately, the moment you have dynamic partitioning occurring, you can't make any of those guarantees. And the issue gets harder depending on what kind of environmental model you have. If you have random failures, you can squint and start saying things like central limit theorem and start hand waving away some of the problems. But if you start thinking about war, or if you have anything where you can have an adversary that has some probability of doing deliberate action against you, it gets to be much, much, much more difficult to model correctly.
Great, yeah. So I would definitely then like to attend your dissertation. I expect that will be announced in the coming days.
If all goes well, yes. CJ was being very polite, explaining about how long I've been working on this problem. I started this problem in 2009, and I basically discovered the problem. It's mathematically chaotic. It's undecidable. I can't remember what the other thing was, but it was basically one of those things where it's been a hard road. It's been a really hard road. So I will give you all the knowledge that I have, but I feel I have very little knowledge to give.
You're being unnecessarily modest. I think there's a lot of
There's a lot of knowledge to learn. There's a lot of knowledge to learn. There's no question about that. I mean, yes, I've learned a tremendous amount, but it is humbling. The problem is really humbling. Don't go into it expecting that you're going to be able to solve a major portion of it. It's a very complex problem. It's not a nice thing to start out with. It is, on the other hand, a very important problem, so somebody's got to solve it. So that's why the Army and DARPA and everybody else keeps going for like sub-T challenge and all the other things you keep saying, is because it is a critical problem.
It is at that.
So I can keep asking questions if other people don't have them, but I guess one thing that you would probably be able to speak to as well in the communications literature is really, I would say, kind of a lack of practical implementation. At least if you read a lot of the connectivity papers that you showed, and I'm just curious, like what thoughts you had on why theory hasn't necessarily translated to practice as it has in some of the other robotic disciplines.
The real issue that I see is oversimplification. You know, you saw it right there in the data mule problem. They simplified to the point that the problem they solved had very little to do with the problem that they actually started out with. And I suspect that happens more often than we care to admit. The other problem is that I've noticed that a lot of stuff is chaotic, meaning that it's extremely sensitive to initial conditions and can be very, very sensitive to minor changes anywhere along the path that it's traveling. If you were a researcher and you discovered this as you were going along, you might decide to change your angle of research suddenly in order to be able to get a paper out. You know, that's my opinion. I don't take that for truth. But that was the feeling that I was getting, is that people were discovering how hard this particular area is. It also means that if you can make some real progress in it, you stake to real claim. You know, you're it.
I have a quick question, and also nice talk, enjoyed it. So at the end of the data mule scheduling problem, you mentioned that one of the big problems is the points of failure with the data mules. Mm-hmm. So I'm wondering if there's been work that you're aware of that's tried looking at this problem, either in the context of benign faults or malicious faults, both designing, like maybe designing a protocol about how, even if you have like a message come in with high, low latency, how you can get some like guarantee of message authenticity or something after some additional amount of time or something like that.
Okay. Are you trying to guarantee that the message was actually from one of your sensors and not a fake message that's trying to drive your data mule to go somewhere else?
Roughly, yeah. I'm thinking about it more broadly in the sense of an arbitrary type of fault. So like if your data mule itself might be malicious, or the sensor might be malicious, but I'm not familiar with this area, so I don't know in what context it's been explored, which is why I wanted to get your thoughts.
I have not seen any literature in the data mule literature specifically kind of about malicious actors. The last papers that I read were years ago. What was it? I forgot the title of the paper. CJ, Dr. Gallier, one of you might remember this. It was about the inability to form consensus with one faulty node in an asynchronous environment. And it was from, I want to say Leslie Lamport came up with it. It's related to the Byzantine generals problem, but it's in an asynchronous context.
Okay. So Byzantine generals problem does handle asynchronous?
Are you sure it handles asynchronous? Because there, like I said, there were two separate papers that were put together. One of them was for a synchronous case and one of them was for asynchronous case. And that's, yeah, I was surprised when I ran across those two papers. But apparently they're fairly well known. If you want to shoot me an email, I can go dig through my bibliography because I've got it floating around over here somewhere. I just can't remember where I put it because it's kind of like, oh, that's nice, and then I moved on. So, as with so many papers, you know, you see something and you don't have time. So,
Right.
Yeah, but okay, I can address bad sensors in one way though. The easiest way to guarantee that bad sensors can't mess you up is by having your data mule wander randomly. Just a total random walk across all the sensors, pausing for a random period of time. It's not efficient, it's not good, but it does guarantee that if you have a malicious sensor that's trying to grab your data mule's attention and hold it, it's unable to.
Okay.
Does that make sense?
Yeah. And what if like the sensor isn't malicious, but just like, I don't know, let's say like there was some problem in transmission. Is there work that looks at how you can verify a message?
Okay.
So like one version of a message gets corrupted going to data mule A, but doesn't get corrupted going to data mule B or something like that.
Okay, but now you're talking about sensors and data mules are both acting correctly, correct?
Yeah, this is a benign context now.
Okay, if this is a benign context, then now we're just signals and systems. You know, we've got forward error correcting codes, we've got all kinds of checksum type codes. It gets to the point where the probability of a bad message getting through is extremely low. So at that point, you end up dropping all the bad ones, and then it's just a linked reliability question. So.
Okay, yeah, that makes sense. Thank you.
You're welcome.
Okay. I guess we have time for a question more if anyone has. I guess, well, I don't want to steal your thunder or discourage people from coming to your talk, but would you care to sort of talk a little bit about fault tolerance, at least in general, and what you've, if in the context of work that you might have seen or lack of work that you might have seen in the area of fault tolerance, and what you're.
Okay. There's a lot of different ways of looking at fault tolerance. I need to broadcast this number of messages out there, and I need to make certain that this long message, when it's packetized, the whole thing gets out there somehow. That kind of encoding scheme, there's many, many different encoding schemes. The best one that I'm currently aware of right now is something called Raptor Q, which is based on a rapid tornado code. What it does is it ends up taking a packet or message of, say, this long, packetizes it such that you have an extra set of packets. So you might only need K packets, but you get M packets out. But the code is very clever such that any K of those M packets that arrive can be used to reconstruct the original message. So now failure and fault tolerance boils down to getting just enough of those packets through. There's fault tolerance where you end up having multiple data mules, and you give the same information to each data mule with the knowledge that data mules either are taking different routes, and therefore if one of them rolls over a mine and is destroyed, the other one managed to get to where it's going, or with the hopes that if one of them has a bad hard drive or something else going on and just forgets your message, then the next one going through will end up picking it up. The problem is when you're talking about fault tolerance, there's it's such a broad field. You have to narrow it down some, you know?
Okay, well, I guess if there are no more questions, I guess we're going to go ahead and thank our speaker, Cem. And nice job.
Thank you.
And I guess we will see you hopefully in upcoming Zooms.
Yes.